Good morning, good afternoon, good evening, everyone, wherever you may be. Thank you for joining our Stantec webinar series today on PFAS. My name is Ryan Radal, and I'm the Marketing Director for Stantec's Water Team in North America. I'll be your moderator today. Just a little bit of housekeeping before we get started. First is that you'll be muted during the presentation, but you are welcome to ask questions through the GoToWebinar questions option. We'll get to those at the end of the presentation with roughly 10 to 15 minutes left. And I'll also give you the ability to unmute yourself with around 5 minutes left if you'd like to comment live or to ask a question live as well. Second, I will follow up with a certificate of attendance that you can submit to your local regulatory agency to try to get some PDH credits for attending this webinar today. Be patient, sometimes it takes me a little bit to get those out, but you'll get one hopefully before the end of the year. And with that, I'm going to turn over to Joe. He's our Director of Research at Stantec and also adjunct faculty at Johns Hopkins, and he will lead you through the webinar today.
Well, thank you, Ryan, and welcome everybody. Today, I'd like to talk to you a little bit about PFAS and some of the stuff that we're doing, as well as some of the issues surrounding these compounds. So I'll go right into it. But before I do that, I would like to acknowledge our team that has participated on the study that we've been conducting. It's a fairly large team. We have a formal strategic alliance with Johns Hopkins, where all our Stantec laboratories are located. And we have, in this alliance, we have a number of both Stantec as well as Johns Hopkins faculty, students, and postdocs. So I won't read their names off here, but I'd like to just acknowledge that they were part of the work that we do and are continuing to do, not just in PFAS, but in many disciplines. We also like to acknowledge the Minnesota Pollution Control Agency, which provided a lot of the funding for the study, as well as the City of Cottage Grove, where we are currently working and is a client of ours. So today, as we talk about PFAS, I'll start off by providing a little bit of background on the subject area. And then we'll take a quick look at the regulations surrounding it, both at the federal and state level. And then we'll look at some of the treatment issues and how to treat for PFAS. Then I'd like to begin to talk about a particular study that I think you'll find interesting that we have started in Minnesota at the City of Cottage Grove, and some of those pilot results that we actually have been obtaining as a result of that study. And then I'll talk to you, I'll summarize, and then also provide you some of our research direction in terms of PFAS and where we've been and where we're going. So why don't we just start right off? And as a bit of background, I'll talk a little bit about PFAS, its chemistry, prevalence, etc. So as you know, we all know that PFAS stands for poly and perfluorinated alkyl substances, the poly, depending on whether the alkane itself is saturated or not with the fluorine molecules. And in general, there are a number of different sources for PFAS. Industry is certainly one. We've all heard of also the firefighting foams, many consumer products, some of the jackets you wear in the winter that contain resistance to wet weather, etc. And then there's also waste infrastructure. And they all contribute to PFAS in the environment. And as a result, over the years, there's increasing interest, and now there's a lot of interest in compounds, on these compounds and their concern or their prevalence throughout the world. It's not a new problem. It actually began back in the 1940s when manufacturing, and the reason it was so popular is because that carbon-fluorine bond is one of the strongest bonds in nature, and is useful for a lot of different manufacturing products. And when we analyze for PFAS, we normally analyze for anywhere from 20 to say 80 compounds, but in reality, there's up to 4,000 to 5,000 compounds that have been released into the environment. So there's a lot of PFAS out there, and many products have been approved for use in our everyday lives that have been that contain PFAS. So the poly and perfluorinated alkyl substances, they contain hydrophilic functional groups and lipophilic fluorinated chains. You see here some examples of various different size chains, but they typically range in length from 4 to 14 compounds, but also talking a little bit about our efforts to go even to the shorter chain compounds, the 3-chain compounds. And then the fluorine replaces the hydrogen atoms on some of the poly, or all of the carbons of the alkane backbone, and that's how you determine whether it's poly or per, so-called, within the PFAS nomenclature. In terms of the characteristics, the PFAS, they can be neutral or ionic substances. They do have unique properties, as we all know. They're very stable to thermal impacts. In fact, to break that bond, you've got to be very, very high temperatures. They have a lot of chemical stability, and they're stain repellents, as well as there is some surfactant behavior associated with them. The neutral PFAS, they're volatile, and they can be atmospherically degraded to ionic PFAS. And for the most part, ionic PFAS are highly water soluble, and they are persistent. And as we know, they're often referred to forever chemicals, primarily because of that carbon-fluorine bond. On the right here, I just show some of the products that they're contained in that circle diagram: shampoos, cookwares, pesticides, firefighting foams, photography, etc. So they are very prevalent. So what are some of the health impacts of the PFAS compounds? Well, C8 Science Panel studies on wastewater that were conducted earlier, they established links between PFOA, perfluorinated octanoic acid, to things like cholesterol and colitis and thyroid disease, some types of cancers and hypertension. So it is associated with several different types of diseases. More recent studies have not necessarily established links between PFAS and cancer. However, one should note that there's a 70 PPT lifetime health advisory, and that's driven by non-cancer health effects. So, as I mentioned previously, there are a lot of drinking water sources for PFAS contamination. I'll just mention the 4 major ones. There's an industrial sources, which is part of the study I'll be talking about today. There's things like military bases that have firefighting foams, and they also are a contributory to it, as well as there are also commercial bases. Then there's landfill leachates also contribute to it, and now we're studying to a great degree wastewater, whether that be in the effluent or in the biosolids associated with wastewater. And they all have the potential to impact our water supplies, whether it be groundwater or surficial water, as well as farms. So how are PFAS regulated? And let me touch a little bit on the federal and state regulations. That'll give you some insights. This first is a map of the prevalence of PFAS in the United States. It was generated by the Environmental Working Group, and at least it gives you an idea of sites that have had PFAS detected at their particular sites. The different colors in this map are the different types of sites that they're associated with. And the main point of this particular map here is just to show that there is a lot of prevalence of PFAS. Many compounds have been since no longer in use, but there are replacement chemistries that are currently in use, and there's a lot of unknowns about those particular replacement chemistries. So in terms of federal regulatory activity, in 2016, EPA issued a health advisory of 70 nanograms per liter for PFOS and PFOA, either as individual compounds or together combined in finished drinking water. And EPA, as part of their UCMR 3, they included 6 PFAS compounds that were regulated. These 6 compounds shown in the table on your right: PFOA, PFOS, PFNA, and then a bunch of other shorter chains such as perfluorohexane, sulfonic acid, PFHXA, and PFBA. And those were all monitored. And they reported that they were detected above the reporting limit in drinking waters at approximately 1.9%, 2.4% for PFOS and PFOA, respectively, in public water systems. And then with the upcoming UCMR, UCMR5, drinking water systems will need to monitor for 29 individual PFAS compounds. And we anticipate that PFOS and PFOA would be regulated under the SD Safe Drinking Water Act. So here are some states with PFAS policies, and what you see here is that the states that you see in orange have actual MCLs that have been promulgated by those particular states, and most of them are in the northeast part of the country. You can see Michigan, New York, Vermont, New Hampshire, Massachusetts, and New Jersey. But there are a whole host of other states which have some kind of protection or drinking water quality policies associated with it. Not necessarily MCLs, but policies. And they can be in the form of advisories, action levels, guidance levels, etc. But these types of policies are gaining momentum throughout the entire country, and I think we'll see more of that, and perhaps more MCLs along that. Okay, with that brief introduction, let's turn to some issues associated with the treatment of drinking water supplies. And what I'd like to go over is just what are some of the current drinking water supplies, drinking water treatment options now, and what are some of those that we may see as promising and actually to fruition in the future. In terms of conventional drinking water treatment, data has shown that there's really little to no PFAS removal capabilities by our standardized treatment. Even the treatment that's associated with things like ozonation really don't make a major impact on PFAS unless they're extremely, extremely, extremely high doses. So to date, I call it conventional wisdoms, as well as some of the data out there, although quite frankly, there's not a lot of peer-reviewed data, but there's a lot of gray literature data, shows that activated carbon, anion exchange, as well as high pressure membrane filtration have proven to be effective for removal of most PFAS compounds. Now, of course, they all have their pros and cons associated with each of these different technologies. And so in selecting which technology works the best or is most appropriate for any type of treatment site, it really depends on a number of things. It depends on the PFAS removal requirements. For some water quality goals, they're associated with just removing it down either to the guidance or action levels or MCLs. And there's other communities that say we don't want any PFAS in our water. And so it's that balance of what your removal requirements are there. It's also dependent on the background source water quality parameters that impact treatment performance. We know that, for example, certain different ions and cations can affect treatment of for example, anion exchange. We know that also high concentrations of various different divalent cations can also impact high pressure membrane filtration and scaling. And TOC can impact most of these processes. So high levels of TOC may need some pretreatment associated with it before it can be employed. Then there's also design constraints, footprint, and process retrofit capabilities. For example, it's anticipated that ion exchange will have much smaller footprint than, say, an activated carbon or a membrane filtration plant. And so those things need to be taken into consideration. Then there's also the operating constraints. One of the biggest operating constraints, of course, is residual management. Remember, each of these technologies are removing the compounds, the PFAS compounds, from the water and now you're left with either another type of waste that needs to be addressed or disposed of. And so when you use activated carbon in anion exchange, and to date, these types of technologies don't or aren't regenerated on site. They're simply a single use and then taken off site and then either subjected to incineration or some type of other treatment. So we're just removing it and putting those residuals someplace. And for high pressure membrane filtration, such as reverse osmosis, of course, you can have a 10% waste stream or concentrate stream that has to be dealt with. And all of these could be potentially considered a hazardous waste. So there's all those issues associated with its handling. Then, of course, there's fiscal constraints, and which makes the most sense from a cost benefit perspective for these technologies. And then, of course, it's necessary to look at for particular waters using either bench or pilot testing to be able to determine which one works best. So there are new and innovative treatment processes that are currently being investigated. Many of these are still at bench, some are at pilot, but they all revolve around two different mechanisms. One is primarily adsorption for the most part, with new and novel adsorbents that are employed. And then others are oriented towards essentially what is the holy grail of trying to deal with these PFAS compounds, and that's breaking that carbon-fluorine bond. So there's things like novel adsorbents, there's porous materials, there's oxidation, there are reduction systems using, for example, hydrated electrons, some ozone fractionation, senolysis, etc. So there are a number of new treatment processes. I think we'll see them. I don't know that they're going to be for application right in the immediate future, but I think we'll see those as time moves on. Okay, what I'd like to switch to now is talk a little bit about the PFAS in Minnesota as an example. And just by a little bit of background, PFAS in Minnesota was an industrial contamination. 3M manufactured and disposed of PFAS in the southeast region of Minneapolis-St. Paul. And then in the early 2000s, the city of Oakdale implemented the first water treatment plant for removal of PFAS because of that contamination. And then in 2017, the Minnesota Department of Health lowered the health-based values for several substances that contribute to the health index, which then promulgated other entities or utilities having to deal with these levels. And so in 2017, the City of Cottage Grove, with whom we worked, constructed 2 interim plant facilities at 2 of their wells. And then finally, in 2018, the 3M settlement was finally adjudicated for $850 million, which will go into addressing the PFAS for all of that area. It's about 150 square miles of plume, and so that'll either go into treatment of water supplies, whether those be at individual facilities, whether there be a regional facility. That's all being determined right now, and so we'll hear more about that as we go. That money also helped fund many several pilot studies going on. And as a prelude to this, this is what Minnesota uses as its way in which to address the health issues associated with PFAS. And they use what's called a health index to track PFAS in drinking water. And basically that health index, or HI, is a sum of the measured concentrations of PFAS in the drinking water divided by their health-based value. And they consider any of that health index when you add up those sums. If it's greater than 1, then it's considered an exceedance. Now on this bottom table, what I have here is all of those particular compounds which are considered within the health index. And you can see that there are 7 in total, but there are only health-based values for 5 of them. So it's really only those 5. Those are PFBS, PFBA, PFHXS, PFOS, and PFOA in that calculation. And I've just given you some ideas here at those bottom 2 lines of this particular table. The raw water, based on their concentration, again, this is just a snapshot, but it gives you an idea of what their what their levels are in relation to their health-based values, and in total the total health index values. So you can see for this particular these particular wells, the health indexes were well over 1 at 2.38 and 3.24. The only other thing I want to point out here is that, and I'll be showing you some of these data going forward, is that for some of these compounds, you can see that they may not impact as the HI value, which is critical to determining whether the water, the treated water is an exceedance or not. Some of these will not impact it as much as others, such as the higher levels associated with PFBA or PFBS will not impact it as much as, say, PFOS, PFOA, or perfluorohexane sulfonate. So keep those in mind, that number one is critical. And what I'd like to do is move on to a pilot study. And our study goal here was to evaluate ion exchange as a potential treatment for PFAS removal as both a standalone process in conjunction with GAC. So with that overall goal in mind, our specific study objectives for this were to demonstrate basically how these particular technologies, IX and GAC in conjunction with IX, behaved or performed, both in terms of operability and performance. And another part was to develop information to develop a policy. And Minnesota calls essentially, state of Minnesota calls essentially a protocol, a policy. There are some differences, but a protocol, as many people would know it, for alternative treatment trains for PFAS removal. And then finally, as with any study, compare the costs and estimates for IX and GAC and mixed treatment. So this is our pilot plant, and this is the general design of it. What we had is initially we had 3 holding tanks. In each of these holding tanks, we needed holding tanks in front of the plant because this was done on a well water, and the well water was often intermittent, and the pumping of the well water is intermittent. So we wanted to have enough water held so that we could run continuously the pilot plant. And then once it's in the holding tank, it would then be fed into pumped into a GAC filter. And in addition, it'd be pumped directly into 2 IX columns, which I'll show you here, and I'll show you a photo in a subsequent slide. And then this GAC filter could be monitored alone. There's able to sample the GAC filter directly, or it would also be pumped into 2 IX columns. And those IX columns would then have GAC treatment followed by ion exchange treatment. And that would be the whole tandem treatment that'd be provided. So it provides a comparison of GAC only, IX only, and then GAC followed by IX. And these are some of the pilot specifications. I won't go over all of these, just to point out a few things. The resins we employed were strong base anionic polystyrenic gels. We used an acid-based bituminous coal for the carbon. This was the same. We chose that particular one because this is the same one that they were using at their full-scale interim facilities. And just to look at some of these pilot specifications in terms of column diameter, you notice that we have a larger column for the GAC as opposed to the IX, and that was because we needed more flow out of the GAC column to feed the IX columns when we were doing tandem treatment. And you can also see the here, let's see, the empty bed contact times. That's another important parameter to point out. For IX, it was 2.5 minutes, and that was basically based on the grade literature that we initially evaluated, and a 10-minute empty bed contact time for the GAC, and that was based on the full-scale interim treatment. Okay, just again, just so it's clear to everyone what treatments were evaluated. Again, we evaluated granular activated carbon only on its own. Then we had IX tandem. So we had GAC pre-treatment followed by IX1 and IX2. Now these IX1 and IX2 are essentially the same as IX3 and IX4 respectively, but the only difference is that IX3 and IX4 had no pre-treatment. So we were actually evaluating the impact of pre-treatment. I might though point out one thing here that's important as you look at the data is that these are obviously dual treatments, and this was a single treatment, and this GAC at 10-minute empty bed contact time represented only the lead vessel in what would be a lead lag configuration if that was ultimately the design. Here's the pilot, our pilot sampling protocols that we employed. In general, we measured 32 PFAS every week. And then on this, I'll show you, we had ports at port 1. We had 3 ports along the columns where we could measure. And so we started off measuring them infrequently, but as soon as we started seeing breakthrough, we normally went down to once per week. We started seeing a little bit more breakthrough. We start measuring at ports 2 and 3. And then we measured some other general water quality parameters here, as well as dissolved oxygen. So here's what the pilot plant looked like. I can see here's the GAC column. And then there are the 4 residence columns. These 2 actually receive water from the GAC column. So they were when you see IX1, X2, you'll see they have GAC pretreatment. IX3 and IX4 receive the well water directly. I should say we did pre-filter the water. I'll talk about that a little later. And then the other thing to point out is that on every column we had different ports, which represent different empty bed contact times. And that allowed us to look at, well, I'll explain a little bit later why that's really important when we're trying to track breakthrough of the overall column. And we'll see some of the data associated with that. Okay, so here's some data generally just looking at differential pressure profiles through each of the columns. And up in various these different colors, you see GAC, the IX, the various IX columns. And when we initially put the columns online, what we initially saw was some rapid fouling of the IX columns, or some of the 2 of the IX columns, I should say, and those were the IX3 and the IX4 that received well water directly without pretreatment. And we started seeing subsequent fouling with the GAC column. And we were a little bit surprised because the iron level was fairly low. It was only 0.15 or 14 at its maximum milligrams per liter of iron. But nonetheless, well, you know, when we did autopsies, we did show that there was substantial iron, at least on the media, as well as on the sides of the column. And what we did is we actually placed in a filter, an iron removal filter, what's called a BERM filter, which is simply a Burgess iron removal method filter. And then once we replaced that in, we were able to get steady state operation. So there seemed to be some fouling associated with iron. And since then, we've also we've actually replaced the BERM filter with one that removes both iron and manganese, which is important to point out because it's important to understand what the inorganics, if anyone's undertaking it, the inorganic impacts of some of the water quality parameters may have on your column operation. But so in general, we've mostly been able to maintain stable operation well under 6 psi. Just a little bit about our sampling. One of the things that was paramount for us is that we get rapid turnaround of our PFAS analysis. And that was because in case we needed to make process changes, we couldn't wait 3 weeks, 2, 3 weeks, 4 weeks for a number to be able to go back and then make a sample change. It was just too long. So at our Alliance laboratories, we instituted a 4-day turnaround, essentially a 3-day turnaround plus a sampling day. So on day 1, we would sample. Day 2, we receive the samples at the lab. We do a solid phase extraction. And then day 3, we would take those extracted samples, put them on our LC10 and mass spec. And then day 4, we would QA/QC the data, would get it plotted, and then we all as a team would discuss the data and again discuss whether any process changes were warranted. This is our analytical suite. We started off with 24 compounds. We're now up to 32 compounds. We added 8 new compounds, and we also added some ultra short chain 3-carbon compounds that we thought may be important. They're here in some of the new compounds. All the new compounds we added are in green. Some of the ultra short ones are like perfluoropropanoic acid or perfluoropropane sulfonate that were added. And there was also had some replacement chemistries for some of the compounds that had been no longer in use, but they were replaced by some other chemistries associated with PFAS. And so we included all the 537.1 EPA method compounds as well as some others here. just a little bit about these ultra short chain compounds and some of the rationale why we used it and why we measured it. Well, we know that breakthrough of these compounds precede the longer chain compounds. And so that gives us a good predictive way in which to be able to look at full column breakthrough. It also gives us a better understanding of the full extent of the potential contamination of the source, and even helps us close to the extent possible the mass balance on the overall absorption process. But in general, these C3 compounds, they're less hydrophobic. They're a lower accumulation potential. Some of these C3 compounds have been reported to have half-lives within the body of the order of 5 to 6 weeks, as opposed to some of the others. And they also have greater water solubility. Okay, so here's the data from our initial snapshot of our PFAS analysis. So in general, of the 32 compounds that we've measured, we've only detected in their groundwater 13 of these 32 compounds. And I have those 32 compounds on the right here with their particular detection limits in our laboratories. And you can see here that there's a whole host of different ones of both the perfluorocarboxylic acids as well as the perfluorosulfonic or sulfonates that you see here. But what's interesting is that one particular compound, you'll see this in subsequent slides, that PFBA, perfluorobutanoic acid, accounts for well, in this case, almost 50% of the overall load. And then some of the short chains, such as perfluoropropanoic acid as well as perfluoropropane sulfonate, they account for about 40% of most of the PFAS compounds. So we have two major sources of compounds, and you'll see that in subsequent slides. So let's go right on to the treatment results and some of the results we saw from the treatment. So what I'm presenting in this table is just one snapshot, and I'll present it in a different way in subsequent slides, but I want to just show you one snapshot of PFAS removal and some of the data that it shows. So here I have the influent levels and the effluent levels, and this is approximately 5 weeks after startup, and I'll present this all in terms of in terms of bed volumes later. But what jumps out at you is that we do get substantial now breakthrough of the PFBA. In fact, in the IX3 and IX4, it's almost reached exhaustion. In fact, one almost might argue that there's, with these higher levels, that may be some desorption going on. And then the other major compound we see is that very short chain 3-carbon compound, which is the perfluoropropanoic acid. Again, almost meeting the influent levels. And then we have some other compounds, but they're fairly low levels, some PFPEA here that we see in some of the effluents here. And for the most part, we don't see many, if any, of the sulfonates. So what does this mean? Well, let's look at that in terms of the health index for Minnesota. And again, I have the same type of presentation in this, the influent and the effluent. And what we see here is that, again, these are these high PFBA levels. And you can see for GAC, there was substantial breakthrough again after about 5 months, but not much for these other compounds. And for the IX that have GAC as pretreatment, we really didn't see anything. And for the IX3, again, we see some of these health index compounds in form of PFBA breaking through, and some of it in the PFPEA breaking through. But if we look at the health index, and remember, 1 is that critical one. Once you exceed 1, then you're out of compliance, that they're well within the compliance level of a health index here. And that's primarily because even though there's a PFPA, the health-based value for the essential levels of PFPA, the health-based value is very high. In fact, if you look at this graph down here, this plots the percent contribution to the health index. What we see here is that this health index is primarily contributed by PFBA, but the ones that are driving will drive the actual levels to a large extent are the PFHXS and the PFOA and the PFOS, because their health-based levels are very low. But you see there were very low levels up here, so they don't contribute much to that health index level. So that's important to understand as we go forward. This plot here shows an example in terms of bed volumes and concentrations of the effluent breakthrough of health index compounds. And this And I'll just focus on this one here, but what it does show you pretty much what the snapshot showed you. We did see some breakthrough of the GAC, as I showed in that previous table, and you can see that it seems to be it seems to have broken through at a similar rate as IX3, but then we really need to wait further for further time to go to see whether this curves off or whether it continues to go straight up. Then the IX only compounds seem to break through next, and finally we have some slight breakthrough of the IX columns that have GAC as a pretreatment. But remember that these particular values are still very low, well below 1. And then you have we can make similar comparisons with each of the other health-based compounds. Again, PFBA, which we see in the most abundance here, you can see a similar pattern to the health-based compound, primarily because they're driving the HI right now, because we don't see a lot of the other compounds. But then you see some of these others that they are starting to break through. The PFO, we're starting to see some breakthrough in the IX3 and IX2, but look at these levels. The concentrations are very low. They're well below 1 nanogram per liter. Okay, so as we move on, let's take a look at some of the intermediate port sampling. And the question becomes is why sample at intermediate ports along the columns? Well, first of all, and probably the most important, it does give us an idea of when we will begin to see breakthrough through the entire column itself. And so from an operational point of view, it gives us an idea when we really need to start sampling in greater frequency from that overall, from the full column. And it also gives us an idea of the concentrations that we might be ultimately seeing as we begin to reach saturation. So this here we can see this is just a GAC profile, and you can see that in the early stages, and I only have these plotted by dates and as C over C0. But what we see here is that there's an initial a breakthrough. We don't see anything happening in terms of the overall column, which is in yellow, and then as the initial through this initial port on the column, we see breakthrough. We start monitoring more frequently, and then all of a sudden we start seeing this breakthrough here, and so we know that it gives us a good indication of what might be going on in terms of the full-scale column. And then obviously when we see the column 1 breaking through, then we also do the same for column 2. And in this for the IX3, let's look at IX4 because it's a little more easier to read. IX4 PFBA profile, again, we have column 1, column 2, column 3, and the full-scale column. Again, they all break through sequentially, and then we can begin to sample. We know when to begin sample through the columns, and then we can really predict or help understand when breakthrough might ultimately become. So it appears to be a good indicator for when we might see a full-scale or a full column breakthrough. But also from an academic point of view, we'll also be able to then begin to better create models to predict this breakthrough that ultimately be used by utilities to look at either pilot or full-scale systems. We can look at the same type of thing through the various different ports, looking at our health index values for PFAS, and this is again only at port 1. And I should mention that, remember, when you're looking at port 1, you're looking at a very different empty bed contact time. So remember I said last time that the empty bed contact time for IX was actually 2.5 minutes. Well, at port 1, it's only 0.63 minutes, so substantially less empty bed contact time. And for GAC, at port 1, it's only 3.3 minutes as opposed to the full 10 minutes. But nonetheless, it gives us an idea of where those health-based values might be going when we should be monitoring to a greater extent in the effluents. You can see here that the GAC in terms of health indices, it breaks through initially, but again, well under, at port 1, well under the 1. And the same patterns for IX3 and IX4. We do get some breakthrough here that occurs even at bed volumes, but seems to be leveling off to a certain extent at 0.2, health value of 0.2 as it begins to reach some type of saturation. And then finally, this is the pretreatment, which breaks through at the latest time in terms of health-based monitoring. So with that, I'd just like to summarize by saying that to date, the treatment studies, and this study is actually an 18-month study, so we're continuing to monitoring, but study removed the 13 compounds effectively, except for PFBA and PFPRA. But in terms of the health index, all the treatments were well below the health index. In general, the sulfonates appear to be removed well by all of the treatments evaluated. And I didn't talk about this a lot, but I did want to mention here that pre-treatment was necessary. In this particular case, that doesn't mean in all cases, but certainly in this particular case, that would need to be evaluated at this point. But at least if you know you have iron and manganese, you should be cognizant of their potential for iron and manganese fouling. Not to say that it'll happen, but in this case, the pre-treatment was necessary in terms of for iron and manganese, in terms of a pre-filter that could remove that. And then finally, GAC followed by X, as I said, was generally the most robust treatment to meet the Minnesota Health Index. But the caveats, as I said, this is a dual treatment, and what we will do ultimately as a true comparison is to do GAC lead lag configuration versus GAC followed by IX. And to me, that's the true configuration of the evaluation. And then just let me end by saying a little bit about what our ongoing research program it looks like. We're continuing the assessment of PFAS removal by GAC-IX and GAC-IX, so that's continuing. We are modeling GAC both at full and pilot scale, and IX at pilot scale for PFAS. If you look at most of the PFAS models out there today, they primarily model up to saturation, but they don't take into account the desorption. So we're adapting these models and with other terms to be able to account for desorption. And then we also evaluate PFAS compounds and PFAS intermediates. Remember, there's 4,000 to 5,000 PFAS out there. So we're trying to look at a wide array of these by using what's called non-targeted analysis. And I'll leave that as that for now. And then finally, in another area we're looking at, we've finished an assessment of over 100 different bottled waters that we've collected and measured for the 32 PFAS compounds. We have a manuscript that'll be coming out on that particular study too. So with that, I'd just like to thank you for your attention and be happy to answer any questions that you might have.
Great, thanks, Joe. We've got a number of questions here, and again, just reminding everybody, you can use the questions option, and I'll also let you unmute yourself here in a little bit if you'd like to ask your question live. So first question is, do you have statistical data that shows geographic locations that require PFAS treatment due to its high level occurrence above the recommended level in the source water?
If I understand the question, they're looking at, is there statistical evidence for different levels within the contaminated area? Is that the?
Yeah, basically wondering, do we have access to data, or maybe that the EPA puts it out, that shows it from a geographic standpoint where PFAS treatment really should occur based on it has high levels of occurrence in the groundwater?
Yeah, especially in Minnesota certainly, and they know they're coming in, they're beginning to understand where those levels are and what may need to be treated. And EPA obviously has been looking at this on a much wider scale. Is it down to the level that perhaps the question intimates? I don't think that's the case just yet, but I'm sure it'll get closer to that.
Okay. And a follow-up on that one, are the recommended PFAS treatment methods implemented in any water supply treatment facilities in the US or somewhere globally? Like, are there operating facilities currently treating for PFAS?
Yeah, there are a number of facilities around the US and overseas. The de facto treatment has been the use of granular activated carbon. And because either there was an emergency notice of that required immediate treatment, and we have a number of examples of that, Cottage Grove being one, where they put in interim GA, they just put in GAC, and there's a number of Air Force bases that just put in GAC for treatment because there was plenty of evidence that GAC was an effective treatment. For ion exchange, the evidence is much less. And I can say we've done a thorough review of the literature. while there's information of ion exchange in the peer-reviewed literature, which we rely primarily on, there's information at bench scale. There's very little, if any, evidence associated with pilot scale. There's plenty of evidence in the gray literature, as well as the vendor literature on pilot scale ion exchange, but nothing in the peer-reviewed literature. So we're investigating that now, and we think that there will be many utilities are investigating ion exchange. So we think that'll come to fruition fairly soon, because some of the treatments seem to be very promising. Just one other comment about an RO. RO is much less of a treatment, even though it can be used in certain circumstances because of all the residuals associated with RO. It's really difficult, and you have a high volume of residuals. It's very and the cost, of course. It's a much more difficult technology at this point to employ on a routine basis.
Okay, and follow up on the cost. There's a question about could we compare the 3 treatment methods employed in the study in terms of cost?
We can't do this at this point because we haven't gotten there yet. We don't have all the breakthrough curves necessary to make those kind of calculations. It is part of the study that will be going on. I have seen a lot of vendor literature that have compared costs, looking at GAC versus IX. And a lot of that is, some show that IX is more cost efficient. Some show that it really isn't. So I to be honest with you, I think it's very site specific, and the jury is still out on that. A lot has to do also with the types of PFAS compounds that are there. For example, if the PFAS compounds that you have are primarily the longer chains ones, and again, maybe not a lot of TOC in the water, it probably would be more cost effective to be able to use carbon, because carbon is very effective for those longer chains. For the shorter chain compounds, they may not be, carbon is not as effective as IX, so you may need to add either longer empty bed contact times or more, replace your lead on your lead lag configuration to a much greater degree. So it may not make sense from a cost standpoint. But in terms of hard numbers, we'll have those that come out of this.
Okay, great. There's a really technical question here from Luke. I might send this one to you offline, Joe, and let you follow up directly, because I'm not exactly sure what he's asking. So Luke, just a heads up on that. Second question here, is there a database for PFAS contamination? You showed that map that showed all the locations. Is that something they're easily accessible?
You can find data in several different places. I know EPA has some. The data that I provided you is with the Environmental Working Group. And they've taken data from other sources and just put it together and put it on a map. And so that's where that comes from. My only caution would be that any data directly generated by the Environmental Working Group, I would be cautious in terms of using that data, and I can explain that in a whole nother chat. But yes, there's not one sole database, but certainly there are database that either from EPA or from 3 or 4 different places that you can collate if necessary. I think the biggest, and there's plenty of data out there on groundwater supplies. Obviously the biggest issue to date is our lack or paucity of data on the wastewater side.
Mm-hmm. Yeah, that leads me to a question here on if there are studies of if there is data pertaining to wastewater. Sounds like it's pretty limited.
Well, there is data. It's primarily state specific. If you go to a place like Michigan, they've really done a good job understanding what their data looks like, not only in their effluent but in their biosolids. And other states, some Northeast states, have also been very active in assessing that. And there are studies now undergoing, one supported by the Water Research Foundation, that is actually looking at both the effluent and the biosolids on a nationwide basis. But in comparison to water, it's very, very limited. And I would say that at this point, we don't have really good occurrence data available to do any in-depth in-depth analysis in terms of directions that we should be going in, particularly as it applies to biosolids, because that appears to be the big issue that will come out of the wastewater side of the PFAS paradigm.
Okay. Let's see, where's the next one here? What media is being used in the ion exchange treatment from our pilot?
One is from down, one is from purifying, and I'd be happy to send you those particular. If you just let me know, I'd be happy to send you the actual product and
sure,
product. Yep, sure.
I'll let you know who asked the question. You can follow up. All right. In a region, what is the best indication that shows the presence of PFAS in water or soil?
I'm sorry, what is the best indication that shows an indication of it?
That shows that there's a presence of PFAS.
Well, I mean, if you're looking at compounds associated with that, I would definitely, if you had a limited way to do it, I would look at the short chain compounds, because I think that's the best indicator, as I showed previously. However, I think the best indicator, quite frankly, is looking at potential first potential point sources that may be contributing to a particular site that is in question, and determine whether that's indeed in a site like in, say, something like a landfill or even a solid waste. You can look at the leach chain. That'll certainly give you a good indication. But obviously, there's no better way than direct measurement. But there's doing a, in the old school, we used to do sanitary surveys. So doing a survey of what might be coming into the area is probably the best way to do it.
Okay. Why does PFBA have a low impact on the health index?
Okay. Well, it's because of the health or the toxicology associated with a perfluorobutanoic acid, and the levels are very high compared to something like, say, perfluoro or PF perfluorooctanoic acid, or even PFHXA. So the levels are high, so you need a higher level to reach a prescribed toxicology endpoint. So as a result of that, when you put it into the health index, because the levels are so much higher than the others, it doesn't have as huge an impact upon that health index, at least in the Minnesota situation, as some of the other compounds. So these are all based on, at least from the Minnesota experience, and certainly it's at least being looked at in many other areas as they begin to set levels, that it's really based on the toxicological information that's available to date.
Okay, good. Yeah, you mentioned you did a bottled water, or we, Stantec, did a bottled water study. Any way you can give people a hint of the results of that?
Well, it's not. It's there. There's no question about it. And there's so we do find it in several bottled waters. There's a lot of bottled waters that they're below the detection limits, but there are a number of them that also have them in them. Many are not much higher than the detection limits. We did find one that was above the actual guidance level set by the International Bottled Water Association, which is set at 10 nanograms per liter of total PFAS. So we are finding it there, so we will be publishing that soon. So it's not like you're drinking absolutely pure water. On the other hand, you've got to be cognizant of the fact that some of them, or most of them, are fairly low levels, and well below some of the drinking water standards. But we should not be comparing directly drinking water standards with bottled water standards. There's too many other differences that occur between the two to make it relevant.
Okay. Very cool. Thank you. All right, we've got 5 minutes left here. I'm going to open up the mics so that if people would like to either follow up on something that I asked correctly or incorrectly, or comment, you can do that yourselves now. So you should have the ability to unmute yourself if you so choose.
I have a clarification.
Yes,
For
please.
the first question. The reason I was asking the occurrence of PFAS was what motivated the study. I mean, are there areas where there are the PFAS occurrence is so high it requires the study? And the second question is, is there an alternative study to protect the source instead of treatment?
Good question. So what motivated the study? As I, at least in this particular, and in many cases, the contamination from the particular industry was over 150 square miles. And the plume has been moving regularly towards towards this area, or has moved essentially. And the levels that were detected in the groundwater basins were substantially high. And as a result, they needed to remove it. Now, the Minnesota Pollution Control Agency wanted to determine whether, well, yeah, we know we can all just stick in carbon, but is there an alternative treatment that can be employed that is either more efficacious, more space saving, or at less dollars? And so that was the major impetus behind looking at that. And then we added the idea that it may be even better to use, or potentially more efficacious to use a tandem treatment of GAC followed by IX. The second issue is the motivation behind, well, is there motivation behind actually addressing the source? In this particular situation, of course, because it was a point source and they knew where it was coming from. And so a lot of those compounds, such as PFOS and PFOA, had been discontinued over time. And so there was, once the source was known, that changes were definitely made. But of course, in many cases, these are legacy compounds that obviously, as we know, persist for long periods of time. And as a result, we're not going to go away in the groundwater. So they needed to be addressed. In all cases, I think the best way to do it is to remove it at the source and not have to treat. So when that's possible, of course, I would advocate at all times, let's look at the source before we look at having to treat. But unfortunately, that's not always the case because of even though many utilities, many industries, or even bases, et cetera, have discontinued for 20 years, the compounds are still there at levels that that pose a deleterious health impact. So it's necessary to treat.
Good questions. Thank you. A couple minutes left if answers anything else. Someone did ask, Joe, you mentioned there were maybe some issues with that environmental working group data. I don't know if you want to get into that, but someone did follow up on that, wondering what those issues are. It's up to you, or we can address that offline directly.
I mean, well, let me just say it's primarily due with the methodologies that were employed, the number of samples that were taken, and the lack of transparency in terms of those methodologies, as well as the lack of peer review associated with the data that was obtained.
Yeah,
so those are some of the issues.
Hi, Joe. This is Luke. My question was really associated with your GAC profile for your PFBA. It was showing the ratio of effluent to influent concentration above 1. So that would indicate to me that there was some preferential desorption going on. Did you see, in a general way, maybe all of the PFAS being absorbed at first and then certain chain length PFAS is desorbing?
It's a good question. Good question, Luke. The PFBA, certainly on GAC, we did see that. You're exactly right. And by the way, it's great to talk to you. I haven't talked to you in a while, but we do see it, and obviously the higher concentration suggests that there is of the and the effluent suggests it's supposed to influence such desorption. PFBA, of course, is a perfluorobutanoic acid, so it's a short chain compound, and we are seeing some of that in some of the other short compounds, such as perfluoropropanoic acid. So I would say, so for GAC, I think it's fair to begin to say that for the shorter chain, it's probably more of an issue. Although we haven't seen a lot of breakthrough of the larger chain compounds in GAC. So until we actually get some empirical evidence, but we know that has a greater affinity for GAC has greater affinity for the larger or the longer chain compounds as opposed to shorter chain. So you would suspect that either the shorter chain compounds would resaturation and then desorb, or even be displaced to a certain extent by other compounds.
Thanks for asking that one wide, Luke. I would have butchered my attempt there. So, all right, we're a little bit over here, so let's wrap it up. Thanks everybody that stuck with it, and lots of great questions. Really appreciate it. Feel free to reach out to Joe directly at the phone number or email there on your screen, and we will be posting a recording of this presentation on our website. Just for those that are looking for a copy of the PowerPoint, because the study is ongoing, we can't actually share that, but we can provide you with a recording. Thanks again. Thanks, Joe, for presenting, and we hope to see everyone on an upcoming webinar. Hope you have a good day.